you real set there?
Yeah.
Yeah. Okay, I think we're going to start, will we? So we're going to kick off this morning. You're later, who's come from Berlin, to tell us something about Hpc Leap.
Thank you, Mike. Welcome, everybody. I learned from the website that last year you already been in Wuppertal and learned something about iterative methods, iterative solvers for large sparse systems. And you probably also learned something about the benefits and the power of those methods, and but also about the limitations. And as an introduction to where we want to go in this small series of lectures, I want to summarize a little bit what you probably already know about interactive solvers. So iterative methods for linear for large systems of linear equations, they can be classified by stationary iterative methods or relaxation methods. This you probably heard about, for example, Jacobi or Gauss-Seidel or SOR. So these two terms, stationary iterative methods and relaxation methods, are used both. And for example, this refers to Jacobi, Gauss-Seidel, SOR. And the other class would be trial of subspace methods. And there you heard about CG, conjugate gradients, or GMS, or by CG star. And these are used, these iterative methods are used in numerical simulations, for example, of partial differential equations. Numerical solution of PDEs. And what that means is one has such a PDE, and this is then discretized and mapped onto a discretized problem, and there one finds that this can be written as a large linear system with some matrix, some solution vector, and some right-hand side, given right-hand side for the solution for this problem. And these problems, the convergence of these methods, typically the convergence and the performance of these methods deteriorates or breaks down when the accuracy of the discretization that goes into this step here, when this is increased. So when we are reaching the continuum limit, mostly these the physical problems that we want to study are given in a continuous space and time, and at the end you want to take the continuum limit, or at least you want to get as close as possible. And in these situations, the performance and convergence of these methods breaks down, and this can be seen from the condition number of this matrix A here. Small kappa of A, and one can show that for these kind of problems, this condition number is proportional to the discretization length, so something like the crit, the lattice spacing, the crit spacing h to the power minus sigma, where sigma now this depends on the problem is some positive integer. And therefore, we see that this will go to infinity for h going to 0. Why is this a problem? Because, for example, look at CG. There we can write down, so we are talking about iterative methods. That means we are interested in a solution, and we get there iteratively, so we have approximations to the exact solution u here, and we also have an error in each step, and you can show that the error for CG in the nth step is in some norm is smaller or equal to the 2 times, and then we have square root of kappa minus 1, the condition number square root of kappa plus 1 to the power n times the error at the beginning of the iteration. And for Jacobi, as an example of these other methods here, one can show that the error of the nth step of the iteration is smaller or equal to, and now it's 1 minus 1 over kappa to the power of n times the error at the beginning, the norm of the error at the beginning. Okay, so we see that since when I have h going to 0, then this kappa goes to infinity, our condition number, both of these methods will stagnate. So these damping, this conversion factor here tends towards 1. And okay, this is an upper limit. It can still be better, depending, as we will see, depending on the composition of your error. It depends whether you saturate this or not. And what we want to do is we want to, for Jacobi, for these stationary iterative methods, we want to understand the origin of this stagnation better. And this will lead us to develop methods to overcome this flaw of these methods. And this, of course, will be multi-grid methods. Okay, so this is kind of a reminder and an outlook where we want to go or what we want to do. Let's start with the introduction of some model problems that we will look at. So of course, we cannot look at all kinds of PDEs and problems in a general way in such a short series of lectures, but so we have to pick something, and of course, to introduce such a complicated method as multigrid, it's best to start with something simple, and we will look at model problems that are simple enough. By the way, please interrupt me if you have any questions. So the first thing you want to look at is, or I want to introduce, is a one-dimensional boundary problem. What does it mean, or what you can think of is, for example, temperature distribution along a rod. This is given by such a PDE. So we have here the second derivative of some function u of x plus the term here times sigma is equal to f of x, where this equation holds in the interior of a line segment 0 to 1. So this is for x 0 smaller x smaller 1. And we take sigma larger or equal to 0. And at the boundaries, this function is fixed. This would be the simplest, or one of the simplest PDEs that you can write down. And now we want to, as I already said, we want to introduce finite differences and a one-dimensional grid. One-dimensional grid and finite differences for approximating the derivatives. Finite differences. So I will always refer to a certain grid with a lattice spacing or grid spacing of h by capital omega, and this is now just line segment from 0 to 1, and then we have here grid points x0, x2, and so on to xn minus 1 to xn. xj here is then of course given as j times h, where j is between 0 and n. And the grid spacing h is given as 1 over n, number of grid points. And this, if we do this with this equation, and I will give you in a second the formula for the how to replace the derivative here, but we already see that since at the boundaries the value of u is already fixed, we will have 1 to n minus 1 unknowns, n minus 1 interior points, and we will have n n-1 equations for them. And they are given as, okay, we have to specify how we refer to u on such a grid. We define uj as u at the point xj. And with this, we can write down the simplest discrete finite difference for the second order derivative. This is I minus 1 plus 2 times I plus u I plus 1 times divided by h squared plus sigma ui fi. Where we use for fi the same identification. And this is now for 1 smaller equal I smaller equal n minus 1 for the interior points. And as I said, at the boundaries, this is fixed to 0. And when you look at such a finite difference discretization of such a PDE, you will see that this can be written in matrix form. And so we have already seen this 1 over h squared, and then matrix form. And then here we have 2 times 2 plus h squared times sigma. Then we have a minus 1 and nothing else on the first line, and then a minus 1, 2 here, and then 2 plus h squared sigma minus 1. 3 entries on the second line, and then this goes on to minus 1, 2 plus h squared sigma. So this is a matrix. This is that is non-zero only on the 3 diagonals on the main diagonal and on the 2 adjacent diagonals. All other entries that are not specified are 0. And this is now multiplied by the vector u1 to n minus 1, and is equal to a vector f1 to fn minus 1. And this can be identified with 1 over h squared times some matrix A times the vector u is equal to f. So now I'm not distinguishing between these continuous functions and these vectors. So this is only to set the problem. We will not be talking about the continuous problem anymore. So whenever you see something like this, it is meant the vector that is made of the value of this u at the grid points. And the same for f. Okay, that would be a one-dimensional problem, maybe a little bit boring. So we also introduce a two-dimensional problem, and then, of course, it can be generalized to any dimension. And we will use only these two. This will be reading. No. Okay. So 2 dimensions. So here we can be quick now, because it's very similar to 1 dimension, of course. Think of the Poisson equation, for example, as a physical application. So we have now 2 directions and 2 derivatives here, plus sigma is equal to f, exactly the same form. This, of course, is now a function of x and y. And we think of units where this is defined. So this equation is inside the unit square. And then we have, again, this is equal to equals 0, and then we have u equals 0 on the boundary. And now we introduce, instead of one-dimensional grid, we introduce a two-dimensional grid, just a sketch. And identify uij with u and xi, xj, and the point xj, xi, yj. So this is yj here. Yj with I times hx, j times hy. So we can have different grid sizes in the two directions, where now, of course, hx is 1 over m, the point in x direction, and hy is 1 over n, the number of points in y direction. And now we have, instead of n minus 1, we have n minus 1 times n minus 1 interior points and the same number of equations. I will not write it down. This is essentially the same kind of discretization. Just repeat this for the one direction and for the other direction. And you arrive at the block matrix form. Which is very similar, of course. Which is very similar. So we have here matrix B, or block matrix B, and we have here minus A times the identity. I specify what identity. Minus A identity, B minus A identity, and this goes on. All other blocks are 0. Minus AI, B minus A identity. This is now multiplied with U1 bar, U n minus 1 bar is equal to f bar 1 f n minus 1. Okay, now I have to specify for you what I mean with B and I and these part quantities. UI bar is nothing else but UI0, UI1, UI n minus 1, this vector, and they are pasted together into one big vector there, and the same for F. And B is essentially given by 1 over hx squared, oh, sorry, y squared, times the one-dimensional A, so the one over here. And both of these are, the D and the I are n minus 1 times n minus 1 matrices. So we have here a block structure that is m by n. So the block structure n minus n by n minus 1. This is the block structure. And then the blocks are given by those matrices here. And in this way, you can construct the matrix for the two-dimensional case. And then, of course, it can be iterated for higher dimensions. One last thing. We can also write down a so-called stencil representation. Of these matrices, where we only specify the non-zero elements and the coupling of that is going on, and this would be for the 1D case 1 over h squared minus 1 to plus h squared sigma minus 1. And in the two-dimensional case, 1 over h squared. Now we assume that we have the same lattice spacing in both dimensions. 4 plus sigma h squared. And here I assume that hx is hy is equal to h. And this gives you the coupling on the grid. So this tells you that this matrix here represents a coupling of this point here. When you're at one point, then the weight of this point is 4 plus sigma times h squared, and then the weight of the 4 neighbors is minus 1, minus 1, minus 1. This exactly gives you the equation here. For the two-dimensional case, and if you look here, this is exactly gives you the equation for the one-dimensional case. Okay, these are the two model problems that we will look at. And now I will turn to these basic iterative methods that I mentioned at the beginning, the Jacobi, Gauss-Seidel, and SOR. We will look mainly. At in examples. We will look mainly at Jacobi, but I will motivate that they are all shared the same kind of properties. First, we need still a little bit more notation. I know that you heard what I will tell you now. You heard probably all of this, but still we need to write it down so that we agree on talking about the same things. So just as a reminder, this is the equation that we are looking at. Now we want to come up with basic iterative methods. And okay, U we will call the exact solution, or we'll specify the exact solution always. A we will assume as symmetric positive definite. Everybody knows what symmetric positive definite is? Terms are of this kind, and now we just set this. We now count the whole dimension as n by n, and then we need norm of a vector, for example, 2 norm. And we will refer to the error. And for this, we suppose you have an approximation of U. We will call V. So V is an approximation of U, and then the error is U minus V. The error is hard to, in a practical situation, it's as inaccessible as the exact solution, of course. So this is merely a theoretical tool. So we need something more practical, and this is the residual. And this is the difference between the A multiplied with V and the true right-hand side F. And of course, this because we know A, since we've just written it down, and in most cases, that where iterative methods are implemented in or used in cases where A is known and easy to compute, and therefore the residuum is always accessible. Of course, if we have a unique solution, then the errors, the residuum will also tell us whether we are converged or not, because phi equals 0 if and only if E equal to 0. But of course, or by the way, or however, if you have a small norm of the residuum, doesn't necessarily mean that the norm of error is very small. From these two equations, we can derive the residual equation, which just tells us that the error fulfills the same equation as the solution. This will be an important relation later on. So, as I said, the error fulfills the same equation as U, but F replaced by the residuum. And now that we've settled this notation, we can derive stationary linear iterations. So you've already heard about this, but I hope I will show you a little bit more details about how these schemes are connected. So from the residual distribution and the definition of the error, we can immediately derive that u minus v is equal to a minus 1 times r. So a is invertible since it's positive, symmetric positive definite. And now we can identify, or we can come up with an iteration through identifying v, our approximation, with the starting, some starting approximation, and u with a new better approximation, hopefully better approximation. So we identify some starting vector of our iteration and u with an update. Then we get an iterative prescription that our new approximation is the old approximation plus some matrix B times the residuum in the at the beginning. Because if we do this, then of course this residuum becomes the residuum for this first vector. And B now, I mean, here in this equation we had a to the minus 1. This is of course something that we don't know, and therefore we need here a B which approximates a to the minus 1. This is another B and the B over there. An approximation to a minus 1 that is easily computable. Otherwise, we wouldn't have won anything. And what you see immediately is that the exact solution is a fixed point of this iteration. Now we can elaborate a little bit more on this equation here on our definition. We just insert the definition of the residuum. The residuum. So if we do this, so I paste it from over there. So our new approximation is the old approximation plus some b times r0. Now if we insert the definition of the residuum, we get b times f minus b0. A times 0. And of course, this can be rearranged, and then you have here b times 1 identity minus b times a applied on our present approximation plus b times f right hand side. And now we define this here as the iteration matrix R. and we can iterate this now here to write down the iterate after n iterations. This is then r to the power of n times the starting vector. And then here we will have a number of operations on the right-hand side that we gather in this function here, CF, and these are a number of matrix vector operations on F. We don't need the explicit form here. And now we can classify the iterative schemes that I mentioned at the beginning with the help of this iteration matrix and this V which appears there. They are all called splitting schemes because you're splitting A into a diagonal minus lower triangular minus upper triangular. So this is the diagonal matrix. This is the lower triangular, and this is upper triangular. And then we have so-called weighted Jacobi. This is given by V equal to omega times p minus 1. Gauss Seidel. This is maybe the easiest one. You just take the diagonal elements to the minus 1, which is of course easy to compute. And then there might be a rescaling. Just Jacobi you have for omega equals 1. And Gauss Seidel combines B plus the lower triangular part, which is also easy to compute by back substitution, or SOR. This is now a variant of Gauss Seidel where you introduce here also a rescaling factor 1 over omega times D plus L to the minus 1. Okay, and as I said, we will have a look at the properties of the easiest case here, and but the properties that we will derive are general enough to also apply to the other ones. Okay, now we have defined our stationary iterative methods. Now we can look at the convergence of these methods. And in particular, we will look at, okay, first we will look at it in general and then on the Jacobi method. And we will understand why it is that the convergence stops. So we have said that the exact solution is a fixed point, but we haven't said anything that these about whether or not these methods converge to the right solution. So, yeah, just as a reminder, exact solution is a fixed point. And now we will write our iteration step here as we use not this version, or we use this version with our iteration matrix. And here we just put some vector g. Since this is anyway only, in one step, it's easy to see that this is only a function of the right-hand side. And if we now insert at this point here u, and remembering that this is a fixed point, we can do this. We subtract the two, and what we get is that the error, because if I subtract the two, then I get the error, and the g cancels, is r time the error in the next step is the error in the beginning. And of course, I can iterate this, and I arrive at the error in the nth iteration is equal to r to the n, our iteration matrix to the power of n, times the error at the beginning. And of course, now I can use any vector norm to derive a bound on the norm and the vector norm and the corresponding matrix norm to derive a bound on the norm of the error and of the nth iterate. This is given as the smaller equal the norm of r to the n times the norm of the error at the beginning.
The g is same in both of the cases.
Here? Yes.
Is it not the number of operations on x that you are doing?
No, I'm not using this equation, I'm using this equation here. And there it's just b times. And this holds then in each step. I mean, you can iterate this. And from this, we can immediately conclude that convergence is achieved if and only if the norm of Rn is smaller 1. You can also show, I won't show this here, that if you have a matrix to the power n and you let go n to infinity, then this is 0 if and only if the spectral radius of R is smaller than 1. Sigma of R is the spectral radius. So this can also hold as a condition for convergence. And therefore, the spectral radius is also called the asymptotic convergence factor, because you can insert this in this equation, and then asymptotically you will converge with the exact solution with this convergence factor.
excuse me.
Yeah.
I have a question regarding the U and V1 that you compared there for the error.
Yeah.
So U is the final solution and V1 is the first iteration.
U1 is the exact solution.
Okay. And V1 is the first iteration.
And V0 is the start of the iteration. And this is the definition of our iteration.
Yes.
And then I use that the exact solution is a fixed point.
Okay.
And this gives me this equation, and then I can subtract the two. So this spectral radius is also called asymptotic convergence vector. And from this you can derive an asymptotic convergence rate. For some base, for example, 10. And this means that 1 over this minus log 10, this convergence rate, or tells you the number of iterations to decrease the error by 1 digit. Okay, so this is in general. And now we will apply this, or we want to apply this to the spectral radius of, we're going to compute the spectral radius for the Jacobi case for the one-dimensional problem. And we will see what it can tell us about convergence and stagnation. Spectral radius of for Jacobi and the one-dimensional problem. We need the iteration matrix for Jacobi, and this is now with an omega because we have this parameter omega in there. This is given now as 1 minus, and then V is just given as omega times d b to the minus 1. And of course, we know the diagonal of A in this case. This is just 2. So we have here omega over 2 times A, very easy. And therefore, we can immediately conclude that the eigenvalues of this iteration matrix will be 1 minus omega over 2, the eigenvalues of A. So we need the eigenvalues and eigenvectors of A. Okay, you might just know them. This is just the two-dimensional, the second order finite difference with certain boundary conditions. So you can easily derive the eigenvalues as 4 times sine squared over k pi over 2n, where now this wave number k here is between 1 and n minus 1. So because of the boundary conditions, we don't have a zero mode. And wkj is now the value of the eigenvector k at lattice site j is given by sine of j k pi over n, where j is between 0 and n. And therefore, we get for the eigenvalues of our iteration matrix 1 minus 2 times omega sine squared k pi over 2n. And when we have a look at this, we see that if we have omega between 0 and 1, we can be sure that the spectral radius is smaller than 1 first. So if this is omega is between 0 and 1, then we have that spectral radius, or the eigenvalues, and therefore the spectral radius is smaller than 1 in magnitude. If we write our initial error as a sum over these eigenvectors, we can decompose them. So don't get confused with the omega and the w. The w are the vectors and the omega is this parameter in the Jacobi iteration. If we write down such a decomposition of our error, then in the nth iteration, we of course have to apply r to the power of n to the error at the beginning, and then this is of course we know how to apply, and then this is lambda k to the power of m times the eigenvector. And here we see that the case mode or eigenvector in the error, in the decomposition of the error, has been reduced by a factor lambda k to the n of our iteration matrix. And this is, by the way, in general. I mean, this holds in general. This is not only to the not only for the Jacobi method. And now, if we introduce some the terminology that we say that low frequency modes, low frequency or smooth modes. If you look at these modes here, if you have a small frequency here, if k is small, then these modes will have a small number of wiggles on the domain. If you have a large k here, then you have it's very oscillating a lot. So low frequency modes are smooth. These are the ones. What time is it? Do I have still a couple of minutes, or is it up already? Yeah,
2 minutes and we're going to take it.
Okay. So we say that low frequency or smooth. This is 1 smaller equals k smaller n half, and then the opposite really up, or oscillating is the rest. And if you look at lambda equals 1 as at the smallest eigenvalue here, and expand this, then you see that this is 1 minus omega squared, omega I squared h squared over 2. And for h to 0, this will go to 1. So that means that no value of omega that you can put here in your method, you have this parameter there, no value of omega will reduce the smooth components of your error. Because as h goes to 0, this smallest eigenvalue here will always go to 1. And therefore, this will not get reduced along the iteration. And this is exactly where this separation of low frequency and high frequency modes, this will lead us to multi-grid techniques, and this will be in the afternoon. Thank you.
So I think since we finished yesterday, you have a break after coffees. So we will. So Bjorn's going to carry on back here at 2, but still, there's coffee and pastries were outside, so let's take a break anyway.
I tried to have them out in James stuff after 3 password pads.